Yes, hello friends. So this is the video editorial for today's GFG problem today, optimal binary search tree. This is a hard problem, and yes, if you do not know the pattern to how to solve this could become a very hard problem for you. So let's get to the problem. You are given a set of distinct keys in sorted order. Although I do not think this is true, I will show you why. Which is represented by keys. Each key ki represents a data record that is accessed during a search operation. For all the keys, you are also given a frequency array frequency which denotes how many times key I is searched for. The cost of accessing a key in a binary search tree is calculated by multiplying its accessing frequency by the level at which it appears at. Therefore, different arrangements of keys in BST gives different total search cost. Your task is to calculate the minimum total search cost required to construct a binary search tree containing all the keys. Okay, so here let's go through this test case. uh, Let me remove this. Yeah, paste this. And what is the frequency? Okay, sorry, what is the keys and frequency? Keys is and frequency is this, right? So see, these are all the arrangements of the binary search tree that we can make, right? So if let's say we go for this arrangement, so there's three keys: 10, 12, 20, and the frequency are 34, 8, 50. So if we do this arrangement, see, whenever we are querying for 10, 34 times, so if we query for 10, so that is we'll go to root, we'll see, okay, root is same, so we'll just return 1. So you will just return true, and how much computation you did, you just did one comparison, right? So that is 10 into 34, right? 10 into 34 plus. Now let's go for this. Let's go for 12. Now for 12 you will go here, you will see, okay, this doesn't match, you will go to right, so you will come here, this matches, so you do two matches, right? So then into 34 do 2 into, and how many times this occurs, 2 into 8 plus. Now for 20 you will come again to 10, you see this doesn't match, you will go to right because 20 is greater than 10. You will come to 12, you will again see it doesn't match, you will go again to right because 20 is greater than 12, and then you will come here. So you did 3 computation, and how many times this you have to do, that is frequency of 20, that is 3 into 50. This is one answer, right? So you can calculate this would come one answer. Now if you did this arrangement, what would be your answer? So if you did this arrangement, that would be that. Okay, so for 10, you will have to come here. You will see it is smaller. You will come here, so it will be 2. This is basically the depth of the node because see, in binary search tree, if let's say we are querying for X node and the depth of X node is D, so that is basically the structure is something like this, and the X is something here which has a depth of D. If it has a depth of D, whenever we are querying for X, we'll actually have to do D comparisons because you will have to do one comparison at the root. Then you will come either if it is greater or less than that, you will come to another node and see if you come to this, you won't go to this. So then again, you will go to the next level. Again, at the next level, you will compare if it is greater than X or it is less than X. If let's say it is greater than X or less than X. Okay, why is this? So again, you will come less than X or less than. So at each level, basically, you are doing one comparison, and the number of levels you have to compare is at T. See, here we saw like for 12, we did two queries, that is depth of this. For 10, we'll do again two queries, which is the depth of this, right? Hopefully, this makes sense. For 20, again, you will, okay, sorry. For 20, again, you will do two queries. For 12, you will only do one query. So what would our answer actually become? The answer would become 2 into 10 plus, or 2 into rather, frequency of 10, sorry. 2 into frequency of 10, which is 34, plus 1 into frequency of 12, which is 8, plus 2 into frequency of 20, which is 50, right? So this would be one answer. Okay. So like this, you can calculate all the answers. Right? You can calculate answer for this, calculate answer for this, and we want the minimum answer. That is minimum number of queries that you have to, or minimum number of comparisons that you have to do for querying all of these frequencies. Right? This makes sense. The constraint here, let's also see the constraint. So the constraint is n, which is basically frequency dot size or key dot size is 100. So n is 100. So how can you solve this? One way is obviously brute force. That is all. Generate all the binary search tree. How you can do this is, let's take each node as the root node. Like take each node as the root node. Then for each of the node at the left, let's take that as the left child. For each node at the right, let's take that as the right child. And then see how, again repeat this, basically do the recursive. And then after generating all of the binary trees, do the calculate the summation and then get this. What would be the obviously this would TLE, because this would be exponential, because you have to make choices. Let's say you are choosing from L to R. Your choice is basically which to take as root. Then if let's say you take I as root, so between L to I minus 1, you have to take one as left child. I plus 1 to R, you have to take one as right child. What I mean here is, see, let's say the keys was 10, 12, 13, 15, 20, right? So if let's say we take 13 as a as a root, 13 as a root, so what would be a left child of 13? That is basically one of these child that is on the left, because it's a binary search tree, so the value has to be less than the root value. So either you can, let's say if you take 12 here, so that is one choice that you made. Then for the, again for right child, one of the values that is greater than this. So let's say we take 20, right? And then this again you will repeat for this part. Not 10 at 12, you have taken 12 as a root. Okay. You have taken 12 as root, so the only value left is on the left child, so you will then take 10. And for 20 we'll take only one value is left, 15. So that is one binary search tree. But again, see, rather than taking 20 at 13, we could have taken right child as 15. That would have given me this binary search tree, right? Yeah. So these are all the binary search tree. You can generate them and then calculate this. But at each you are making some choice. So this would go as, I think, in factorial frequency, right? I'm not 100% sure, but obviously this would TLE. This is not the most optimal solution. Okay. How can you optimize this then? Is, see, we are going with the same constraint, or the same logic, that whenever we are at L to R, we have to take one as root. Let's say I we take as root. Now, what would our answer be? Let's say our answer is basically, uh, let's call a recur function. This recur function is basically when we are first calling it for L to R. Right now, basically for I equals to L, I is less than R, I plus plus. Right. So basically, we are choosing one as root. Choose root. Now our answer is minimum of answer, comma, recur L, comma I minus 1 plus recur I plus 1, comma R. So again, as we saw here, we take one as root, then we have to solve the case for this. That is what is the minimum cost of all the values on the left. That is basically you choose I as root. Now you have to choose for L. That would be 0 here, 0 to 1. That what is the minimum cost for these things, and what is the minimum cost of these things. So that is taking I as root, are basically so you take I as root, then your left subtree will have values from L to I minus 1, and your right subtree would have values from I plus 1 to R. Then we'll again call the recur function only and check what is the minimum operations that you need to do for this, minimum operation you need to do for this. Now the only caveat here is, see, you have to return not answer, but answer plus total frequency L to R. Why? Because see, okay, let's take this case only 10, 12, 13, 15, 20. Yeah. 10, 12, 13, 15, 20. Okay. So taking 13 as root, let's go 10 and 12. Let's say these guys return 20 as their right value. Let's say these guys return 30 as their total value. and the total frequency is something like 7, 3, 4, 6, 10, right? Something like this. So the left answer I get is 20, the right answer I get is 30. What would be our total answer? Our total answer would be left answer plus 30 plus this answer, or the sum of this, that is 30 here. Why would this be the case? Because see, uh, yeah, when I call, see, for 13 I will call this, right, 10 and 12. When I call 10 and 12, uh, what I'm assuming here is that this is our 3. The 3 is only 10 and 12 having the values, and this what is the minimum answer I can get by rearranging these values. That is what I'm getting. Again, similarly for 15 and 20, I'm assuming that my 3 only has 15 and 20, these two values, what is the minimum answer I get. But that is not the case. The case is that 13 is also there. So for 13 is also there, so all of these like 20 would be 20 plus the sum of frequency in the left, sum of frequency on left. Because as I said, all of these depth are now starting from 1, but that is not the case because the depth should start from 2, because 13 is root. So that if 13 is root, all of these depth would increase by 1. So that is number of times that the query is there. So 20 plus frequency of L plus frequency of I, or basically this is I to L minus 1, I to L minus 1 plus frequency of I, because see, this this as root, this means that this has to get queried one time, right? This gets the depth of this is 1 plus right answer, basically left answer, let's say left answer plus right answer plus summation of frequency from I plus 1 to R. Now see, we have frequency of I to L, sorry, L minus 1 to I. This is L to I minus 1, I minus 1. This is frequency of I, this is frequency of I plus 1 to R. So this just becomes total frequency, right? Combining these three, basically answer becomes left answer plus right answer plus total frequency. So this is actually a very uh, very popular pattern called MCM, which is matrix chain multiplication. So you can actually solve using the same pattern, MCM. So what is you can also solve the matrix chain multiplication problem using this pattern. The pattern is basically, it's a DP pattern, that the answer for L to R. So what's the pattern here is, see, you are given this L to R, you will call recur 0. The final answer would be recur 0 comma n minus 1. This is the final answer. This answer is basically that, see, you have to divide this into parts. You have to divide left part, you have to divide right part, and you have to take one value as middle, right? So that is, and the final answer is left answer plus right answer plus the cost of breaking this down. So the cost of breaking this down we saw is the total frequency. So that doesn't depend on I. In some question that would depend on I, the cost of breaking this down. So answer is basically minimum over left answer plus right answer. This is the MCM pattern I'm talking about, plus cost of breaking this down, cost of breaking. And again, this left answer and right answer we will calculate recursively. Now, what is the key here is, see, number of changing parameters are L and R. So you can use DP of n square states, because two parameters are changing. We'll have to maintain DP I comma j. But what would be the time complexity? Time complexity would actually be, because as I said in earlier videos also, in time complexity of DP is basically number of states into transition time, and transition time number of states is n square and transition time is n here. Why is it n? Because see, at dp I L comma R, you are going for all I in L to R, right? In L to R, so that is, you are doing n computations. That makes transition time n here, so that would become n cube. But the n cube is fine because n is 100, n is 100, so n cube would be 10 to the power 6. That is fine. Yeah, hopefully this makes sense. We can jump to the code now, like all of this pattern and these things. Yeah. Let's go to the code. If you have never implemented MCM, you can look to the code and then try to implement it on your own. It would teach you a lot, I guess. Yes. So one more thing I will show you when we submit this. But yeah, so basically I create a pair of int comma int arr. We can just pass the keys and frequency. I will tell you why I created this, and I sorted this arr dot begin dot arr dot begin. So I didn't actually read this part. I missed this by mistake, that the all the keys are distinct and in sorted order. If that was the case, there is no point of creating this arr which is keys comma frequency. I just did this because I thought the keys would be in random order, and then I have to sort this. So the problem here is actually if I submit this sorting code, this would give wrong answer because I do not know how this is possible. But the question says that all the keys are distinct and all the keys are distinct and in sorted order. But obviously, you can see here the keys are not distinct. See, 26 is there, 26 is there, and this is not even in the sorted order. So because I am actually calculating the correct answer because I am sorting this ARR dot begin and ARR dot end, so that is actually giving the wrong answer. If I remove this, then I am getting the right answer. I think that test case is broken. The GFG should properly fix this. Like this is weirdest thing I've ever seen. The test case is wrong. It's clearly mentioned here that keys is where is it? Distinct keys and sorted order. I do not know. Maybe I'm missing something. Let me know if I'm missing something. Yeah. So okay, I create this ARR. It's not really necessary because the assumption of distinct keys and sorted order. Then I create, see, DP would be of I comma j, and I and j both can be as 100, right? So I create 100 comma 100 size 101 comma 101 size 2D DP array. I set all of them to -1. As I said, we'll call 0 comma n minus 1 here. So if L is and R is, so this is a base case that you only have to break one value down, right? So base case is something like you only have one choice here. So if this is like 10 and 10, so the final answer would just be 10, right? Or the frequency of this 20. Let's say if the frequency is 20, so the final answer would just be 20. Right, this is the base case. If L and R is there, so you just return the frequency of ARR L. The second base case is that L is greater than R. So this is basically when this could happen is, see, if the if let's say 1 2 3, this is there 3 or 0 1 2, like these are the values you want to break, and you say that I'm going to take 0 as my root. So what would be our left would become 0 to -1, right? Because left is L to I minus 1. So 0 to I minus 1, that is left is basically null here. So you can either check that if the range is valid on breaking it down, or you can just add a base case that if you go through an invalid range, you just return 0, because see, you do not have to break any values here. So that is what I'm doing. Is basically I'm not checking here if the L or I minus 1 is valid. I just go to it and then we'll see if the state is not valid, we'll return 0. And as I said, we'll take each node from L to R as root node, and we'll get the C answer as left answer plus right answer. And the answer will store the minimum answer, and total frequency would be the ARR I dot second. And as I said, the cost of breaking this down is always total frequency. So the final answer would be answer plus total frequency, and we'll store this in our DP. So this is basically memorization, and this would work. I can submit this. Hopefully, you were able to understand. I think you should implement MCM first before solving to this, and read through and try to solve this using the same pattern. If you were able to solve this, then come back to this problem. This would become very easy for you guys. Yeah, thank you for watching. Bye bye.